Today we are talking about graphing exponential and logarithmic functions, and we're going to start by talking about these two functions. So this equation is an exponential, it has a base and an exponent. This equation is logarithmic, it has a base and it's written as a log. And we talked briefly earlier in the unit about how the logarithm function and exponential are inverses of each other. So I'm going to take a minute and just talk about that up here. So here's an exponential function, my base, my exponent, and it equals this value y, okay? We know that inverse functions are when you take x's and y's and switch their places. So I'm going to do that here. X equals 2 to the y. And now I'm going to solve for y so I can get this equation written as a function. And we learned when solving and working with our log properties that we can rewrite this situation as a log where my base is 2, so log base 2 of x is my argument equals the exponent y. So log base 2 of x equals y. So now we have y equals log base 2 of x. So you'll see that that is this function right here. And we're going to create xy tables for these two equations. We're going to graph both of them on this coordinate plane and see how they compare to each other and what properties are happening. So for this first one, we're going to create this xy table. If I plug -2 in here for x, I have 2 to the -2. Our negative exponent rule says that means to flip the base, so 2 becomes 1 over 2, and change the sign on the power, so it becomes +2, and that's going to give me 1 over 4. Then when I plug in -1, again I'm going to flip the base, change the sign on the exponent, and this is 1 over 2. When I put 0 in there, I simplify to 1. When I put 1 in, I get 2, and when I put 2 in, I get 4. So I'm going to graph this and see what it looks like. So I've got a point at -2, 1/4, and then -1, 1/2, 0, 1, 1, 2, and then 2, 4. I'm also going to put 3 in just to talk about something. If I put 3 in, I get 2 cubed, which is 8. So I want you to notice how the first few points were really close together, and as x starts to get bigger, the points spread out further and further and further. This is something that we call exponential growth. And as x goes to -infinity, the y values will get smaller and smaller, because think about our fractions right here. At -1, my denominator was 2. At -2, it was 4. At -3, the denominator will be 8, and so forth and so on. So the top will stay 1, but the bottom will get bigger and bigger. That means it's approaching 0 because the y value is getting smaller and smaller forever. But it's never going to equal 0, because there's no x value I could put in here that would make this function equal 0. So what that means is we have a horizontal asymptote right here. Okay, let me write that down. Horizontal asymptote at y equals 0. And then if we look at these three values right here, we can notice a pattern. Regardless what my base is, because my base could change. This could have been a 3 or a 4, an 8, whatnot, okay? These 3 points right here, we can generalize some values. We can generalize that anytime x is -1, its y value is going to be 1 over whatever the base is. Anytime x is 0, the y value will be 1. And anytime x is 1, the y value will be whatever the base is. And so we could get these 3 points very quickly from any exponential function. Okay, now I'm going to use a different color to talk about the log graph. We don't need to do any math to make this table because we just talked about how these are inverse functions, and that means we're just going to switch their x's and y's. So I'm going to take a minute and take all these y's and fill in the x column with them. And then I'm going to take all the x's and fill in the y column. And now I'm going to graph those. So now I'm graphing the logarithmic graph that has a base 2. And we would also have a point at 8, 3. That's not part of our table though. So here's how log looks. And in this situation, we don't have a horizontal asymptote, we have a vertical asymptote at x equals 0, which is right here. So please understand this is two separate graphs that have just been put on the same grid. Okay, they're not two parts of the same graph. We finished doing rational graphs last unit. This is not that. It's two completely different graphs we've just put on the same grid so we can compare them to each other. And then one thing I want to note is that because these graphs are inverses, they have a reflection over this line y equals x. So here's my exponential graph and here's my logarithmic graph. And you'll notice they're both increasing as x goes to positive infinity. So as x goes to positive infinity, my y values are increasing here. Same thing on log. As x goes to positive infinity, my y values are increasing. And then the general points that you can have like these little tiny formulas for on log are the same as exponential, just backwards. So 1 over b where y is -1, 1 when y is 0, and b when y is 1. Right? So we're going to take a minute down here and do the same thing for base 10. So this little paragraph here says, one base that your calculator uses is base 10. When you see y equals log x, so notice there's no base written, it is assumed that you are using base 10. This is what is known as the common log. We're going to fill in the tables and graph both of those functions. So I'm going to do my 3 general points first. When on exponential, when x is -1, y is 1 over whatever the base is. And here the base is 10, so it's 1 over 10. 0 gives me a y of 1, and 1 gives me a y value of b, the base, which is 10. Plugging in -2 gives me 1 over 10 squared, or 1 over 100. Plugging in 2 for x gives me 10 squared, or 100. So 1 over 100 is approximately 0.01, and 1 over 10 is about 0.1. That's going to be really hard to graph on here, but we're going to try. And then don't forget that exponentials have a horizontal asymptote of y equals 0. The log table is all these values flipped. So we've got 0.01, 0.1, 1, 10, 100, and then -2, -1, 0, 1, 2, and a vertical asymptote at x equal 0. So remember that this is a log. When there's no base written, we know it's base 10. So I want you to pause your video and take a minute and graph those over here. Okay, here's what those graphs look like. The blue one is exponential, the red one is the log, and one more reminder that this is not one big graph. These are two separate graphs that just are on the same coordinate grid. Okay, let's look at the back of our notes. We have one more section of filling in an exponential log table and graphing. And here's another special log that we have. Another base that your calculator uses is base E, where E is approximately 2.718. It is an irrational number like pi. So E is not a variable. It's a symbol that represents this number, 2.718. It goes on forever and never repeats. When you see y equals ln x, it is assumed that you are using base E. This is what is known as the natural log. So when you see ln x, it's the same as log base E of x. And E is approximately 2.718. So when I go to plug these exponents in for e to the x, I'm actually going to start with these three. If I have a -1, I know that its form is going to be, so this is what we wrote on the front of the notes. If you have -1, your y is 1 over the base. So my base is e, or 2.7. So this is 1 over 2.7, wait, sorry, I want it to be right here. 1 over 2.7, which is approximately 0.14. 0 gives me a y value of 1, and 1 gives me a value of 2.7. When I plug -2 in, it gives me 1 over 2.7 squared, which is approximately 0.14. Oh, I'm so sorry. The problem is I'm rushing, and then I'm making mistakes. This is 0.37. And then down here we have 2.7 squared, which is approximately 7.29. And don't forget there's a horizontal asymptote at y equals 0. So then flip those values for the log table and then graph both of them over here the best you can. And then pause your video to do that. Okay, check your table with mine. There's an extra row in that table for no reason. And then here are the graphs. I know that those values are really close together. Just do the best that you can. Okay, I'm going to make a separate video for the last two problems where we applied transformations to graphs.